Alright, in this video we're going to take a look at experiments and observational studies. An observational study is when researchers do not impose a treatment on the experimental units. All they're doing is simply observing. So this would be, an example would be like a survey. Alright, there's two types of observational studies. There's a retrospective study, which we select the experimental units, then ask about previous behaviors and conditions. And there's a prospective study where we identify the experimental units in advance and then collect data as events unfold. So basically you're following them and then recording the data as things are happening. Alright, type of study. So example 1, researchers looked at records of tenants at an apartment building over the past 5 years to determine if the landlord had a preference in the race of his tenants. So they're going and they're taking the records and then they're looking back. So that's retrospective. Example 2, a local school identified 50 kindergartners who are considered at-risk students and tracks their progress through high school graduation to see if the programs already in place in the district help these students. So this is a prospective. So we're identifying them and then we're going to follow them from kindergarten through graduation. Alright, experiments. An experiment, we impose a treatment. We manipulate factor levels to create the treatments. We randomly assign subjects to these treatments, and we compare the responses of the subject groups across treatment levels. Experimental units are the individuals on which an experiment is done. So that isn't always people. It could be animals, cars, plants, whatever it is that you're doing the experiment on. Subjects is when we're referring to human experimental units. So if it's humans, you'll hear the word subjects. Factors are explanatory variables or variable levels controlled by the experiment. Oopsies. A level is the specific value a factor can take, and treatments is a combination of levels of each factor, the specific thing that can be done to each group of the experimental units. So if you don't have different levels of the factors, then it will just be, the treatments will just match your factors. But if you have different levels, then that may be different. Alright, example 3. You work for a botanical company and with your team you have developed a new type of plotting soil, specifically designed to improve growth and development of roses. An experiment needs to be designed to show that your soil works well compared to leading competitors. How can you design a good random experiment? Alright, so I'm looking for something that measures the effects of, we'll say, 2 fertilizers and 3 water amounts on the plant growth. So I'm just picking these. Those might be the things that I'm using. My factors would be fertilizer and water. So the different type of fertilizer I use and the different amount of waters. The levels, well, for fertilizer, I would have fertilizer A and fertilizer B. As I said, I had 2 different fertilizers. And I would also have, for water, as one of my factors, the levels would be 100 milliliters, 200 milliliters, 300 milliliters. So those are examples of how your factors can break up into levels. And then my response variable would be the height of the plant, maybe the width of the plant, maybe the number of buds on the plant or the number of leaves, or maybe just the color of the plant. How are you going to be measuring which one's better? Alright, principles of experimental design. The control as many aspects of the experiment as possible. We want to also reduce and anticipate the effects of lurking variables. And we want to use a control group if possible. So lurking variables are other variables that are identified in the experiment, but could maybe have an effect on the results. Randomization. Randomly assign experimental units to treatment groups. You want to assign each experimental unit in the sample as a number. So give each sample a number. Then use a table of random digits to assign the experimental units as evenly as possible. It's not always going to be 100% even, depending on the numbers you start with, to their treatments. Or you could put all the experimental units in a bag, shake, and then pick to assign them to treatment levels. Replication. Repeat the experiment on many different experimental units. Also, repeat the experiment on many different samples of the same population. Replication helps show validity of the results. If you replicate and see the same or similar results, then you know that your experiment is a little bit better. Alright, a control group. Experimental units assigned the baseline treatment. So this may be where they get no treatment at all, or it's the old treatment, or a placebo. Alright, a placebo should be used if experiment has subjects. So remember, subjects are human beings. So if it's being done on humans, then there should be a placebo when we're designing the experiment. A treatment known to have no effect, so it's a dummy treatment. An example would be like using a sugar pill instead of aspirin. Okay, and with a placebo, there's something called the placebo effect. It's the tendency of human subjects to show a response, even when administered a placebo. So, example, people taking a sugar pill instead of aspirin tell their doctor that their pain has decreased. This is because their minds have convinced their body that they are feeling better, and their body shows the response. Alright, so we're going to get into different designs, experimental designs. So we have a completely randomized design. Randomly and evenly assign experimental units to treatments. So our example, 36 rose plants. We're testing 3 different types of soil, and we're measuring the size and health of the plants. So I'm starting with 36 rose plants, and we're going to make kind of like a tree design, tree diagrams. Alright, so 36 rose plants, and I'm breaking it up into 3 different types of soil. So I'm going to randomly assign those 36 into soil A. We'll have 12 there. Soil B, there'll be 12 in that group. And soil C, there'll be 12 in that group. And those are randomly assigned. Okay, and then sometimes you'll want to put like random or like a little star on those lines that you're breaking up, and then describe how you randomized. Alright, and then after I do that, I'm going to compare the size and health of the plants. Alright, blindness. A single blind study is when one group, or a single blind experiment, one group of the experimental units or the researchers recording the results do not know which experimental units are getting which treatment. A double blind is when both groups, the experimental units and the researchers recording the results, do not know which experimental unit is getting which treatment. Blinding can help to reduce bias when possible. Okay, so sometimes that might be helpful. If you know you're getting a placebo, then you might not take it as seriously. Same with a doctor. If the doctor knows that you're taking a placebo, or whoever's treating you or collecting the data, if they know that you're taking a placebo, they might not treat you or collect the data as effectively. Alright, your turn. Number 1. I want to test out a new plant food. So I take 20 plants and give half the new plant food and half no food at all. All of the plants get the same amount of water and sunlight each day. After 30 days, I measure the height the plant has grown, and also how many flowers it has on it. So my individuals are the 20 plants. My factors are food. So I have no food, or the new food, or no food. My treatments are the new food or no food, because there are no levels, no different levels. My response variable is the height and number of flowers. So I'm going to make my design. So I have 20 plants. I'm going to randomly assign those 20 plants into either the new food, there'll be 10 there, or no food, there'll be 10 there. And then I'm going to compare the height and flowers. Alright, your turn, number 2. High cholesterol levels in people can be reduced by exercise or by drug treatment. A pharmaceutical company developed a new cholesterol-reducing drug. Researchers would like to compare the effects of the new drug with the currently used and accepted drug. 100 volunteers who have a history of high cholesterol and who are currently not on any medication will be recruited to participate. So, what are the treatments and what are the subjects or individuals? Well, the treatments are the new and the current drug. And then my subjects are 100 volunteers with high cholesterol. The response variable is their cholesterol level. And then would a placebo be appropriate or necessary? Why or why not? Well, yes, if we're talking about human subjects, we want to include a placebo. Also, when you're doing something with drugs, you want to include a placebo. Alright, so designing the experiment, we have 100 volunteers, and we could either give them the new drug, the current drug, or a placebo. So I'm going to randomly assign them to either the new drug, the current drug, or the placebo. And because I have 100 volunteers, I'm going to have an uneven amount. So I'm going to do 33 to the new drug, 33 to the current drug, and 34 to the placebo. And if those numbers work out differently, then that's fine too. But you want to be as close to the same as possible. Alright, and then I would compare my results. Well, I'm comparing their cholesterol level. Alright, a two-factor design. So, for an example of a two-factor design, we have 36 rose plants, testing 3 different types of soil and 2 amounts of water. None or once a day. So for the water, they either get water not at all or once a day. Still measuring size and health of the plant. So I have 36 rose plants, and I'm going to randomly assign them to 3 different types of soil. Soil A, I'll have 12 in that group. Soil B, I'll have 12 in that group. And soil C, I'll also have 12 in that group. Then, out of the 12 in soil A, I'm going to randomly assign them to either get no water or water once a day. So, water, none, would be 6 of them. And water once a day would be 6 of them. And I would do that for soil B and soil C. Then I would compare all the results. So I'm comparing the size and health of the plants. Alright, block design. So using blocking, block is a group of similar experimental units that would have an effect on the results. So an example may be gender, age, breeds, etc. So block the roses that we have used before based on the type of rose. So we have an alba rose or the rock rose. So I would start with my 36 rose plants, and I would break them into the alba rose and the rock rose. Now when we're blocking, I don't know how many of them are alba and how many of them are rock. It didn't say that I had an even amount. So the number pieces just kind of go out the window. If they give you specific number values, then you can include that in your design. Alright, and then I would break them into my 3 different categories, my 3 different treatments, A, B, and C, soil A, soil B, soil C. And then I would randomly assign those in each block. Then I'm going to compare the results, compare the size and health for the alba roses, and compare the size and health of the rock roses between the 3 different treatments. And then I would compare the size and health overall. Alright, so your turn. Let's go back to the experiment on people with high cholesterol. We want to test the effects of a new drug and old drug. We also thought a control group would be useful. There are 100 volunteers with high cholesterol and that are currently not on meds that are available. So we have 100 volunteers. Our treatment is the new drug, old drug, and the placebo. My response is the cholesterol level. And then some of the lurking variables in this experiment could be the amount of exercise that they're getting, the diet that they're on, their genetics, their gender, their age. Those are some examples of what might be lurking and kind of changing the outlook of the response variable. So I'm going to use one of these variables to block my design. And I'm going to go ahead and use exercise because exercise has different levels. So I have 100 volunteers, and I'm going to block them by low exercise, medium amount of exercise, or high level of exercise. So the people that don't really exercise will be in the low exercise group, and the people that exercise frequently will be in the high exercise group, and so on. Then from each block, I will break them up, and I will randomly assign them to either get the new drug, the old drug, or the placebo. So the new drug, the old drug, or the placebo, random for everybody that has low exercise. The new, old, and placebo for medium exercise, and same for high exercise. Then I'm going to compare the results within that block. Within each block, I'm comparing the results. And then within all of the blocks, I would compare the results. So I'm just going to use this little asterisk sign, and that's going to stand for compare cholesterol levels, so that I'm not writing the same thing over and over and over again. All right, so if you're going to use some sort of a symbol, make sure that you have a key so that the AP graders know what that symbol means. But remember, it is a time test, so that is something that you may want to consider. All right, your turn, number 4. Men and women respond differently to advertising. An experiment to compare the effectiveness of 3 TV commercials for the same product will want to look separately at the reactions of different genders and assess their overall response to the ads. There are 70 people available for the experiment. What are some lurking variables in this experiment? Well, gender is one. And so we're going to go ahead and use that to block, to reduce the variation. So I have 70 people. I'm going to block them into men and women. And then I'm going to have randomly assign the men and randomly assign the women to watch one of the 3 commercials. So commercial 1, commercial 2, or commercial 3. And that will be random. Same for women. Commercial 1, commercial 2, or commercial 3, randomly chosen. And then I'll compare the results within the blocks. So I'm comparing their reactions to the commercials. And then I'll compare the results between the 2 blocks. All right, a matched pairs design usually only has 2 treatments. Each experimental unit gets both treatments. And we randomize which treatment comes first or second, or goes on the left or the right, or the front or the back, something like that. It can also be where 2 subjects with equal characteristics are given different treatments and then compared. So, like, for example, like twins that have the same genetics. So, an example would be an example of a taste test. So, Coke versus Pepsi. We have our experimental units who we're doing this experiment on. I have treatment 1, they're going to get the Coke first, then the Pepsi. And treatment 2, they're going to get Pepsi first, then Coke. And they will be randomly assigned to which treatment group. Then I will compare their results within each treatment and then across the treatments. All right, your turn, number 5. We want to test the effectiveness of 2 types of tires. Call them A and B on cars. We gather 50 different cars from our experiment. We will be measuring the amount of wear on 2 types of the tires. The cars will be driven normally for 3 months. How could we best design the experiment? So, what are the individuals and what are the response variables? My individuals are 50 cars. The response variable is the wear amount. The treatments are tire A and tire B. In my experiment, I'm starting with 50 cars, breaking it into 2 treatments, randomly assigning them. So treatment 1, they get tire A on the left, and they get tire B on the right. And that would be 25 of them. Treatment B, they get tire A on the right and tire B on the left. And again, 25. And with the matched pairs, you want to look at the results within treatments and then across the treatments. And I'm comparing the amount of wear on the tires. Alright, your turn number 6. I want to go back to the car tire experiment. Suppose the cars were different, so different types, SUVs, sports cars, sedans, trucks, etc. How would you reduce this lurking variable of car size and type? So I would use blocking. So I'd take my cars, I'd block them into whatever categories, SUV, sedan, truck, sports car, whichever. And then I would give each, randomly assign them to their treatments. I'd compare the results within each treatment. I'd compare the results within each block. And then I would compare the overall results. Alright, the best experiments are usually randomized, double-blind, comparative, and placebo-controlled. And then some more vocabulary that we've kind of talked about throughout this video. Confounding is when levels of one factor are associated with the levels of another factor, so their effects cannot be separated. A lurking variable is a variable that has an important effect on the relationship among variables, but is not included in the study or experiment. And statistically significant is seeing an observed result or difference so often that it is most likely not due to chance, and instead is a true response in the study or the experiment.